Hello fellas, and you are staring at yet another LED driver. I actually have another video about a more powerful LED lamp and I will upload it first, then I'm gonna upload this video that you see now. So if you see this video, there must be another video that describes my previous version of this LED lamp. This you can see is a drive which is kinda tacked together and not the most beautiful thing in the world, but hey. This method of construction allows me to make a very rather compact circuit. You can see no holes whatsoever. Design planned on a piece of paper, none of that CAD rubbish. You can see that's where I planned the layout with all my symbols and stuff like that, and believe it or not, it works just fine. You can see the construction. Heart of this device is a little bit different to what I used in previous lamp. In previous lamp I used tiny switch 267 and here is tiny switch 278, which is more powerful version. And in this particular case it just doesn't give a crap on that about that kind of load that I'm putting onto it. So anyway, here you can see quite a beefier rectifier than in previous version. This is a surface mount Schottky diode, 3 amp forward current rated and 100 volt reverse voltage rated, so more than enough. Current in this particular case is about just shy of 0.6 amps in cold state and half an amp in hot state. Why is that? Well, if you look at the schematic, you can see that current feedback is implemented via this transistor and this current sense resistor, so that's what is responsible for the constant current section, for feeling the current, sensing it. And if you might know, the transistors are very temperature unstable. Their parameters drift a lot with temperature. So the thing going here is current passing through this. You can see it goes like this through the LED, goes through this resistor, through this resistor, and of course you will have some heat generated in these resistors, okay? So that heat heats up this transistor, and that decreases its base emitter voltage drop, and its base emitter voltage drop is what actually determines output current. Output current of this device is determined by this very simple equation: base emitter voltage drop divided by this resistance, and that's it. So resistor gets hot, heats up transistor, voltage drops, so is the current. Very simple, not a rocket science at all. So you can see this construction, this LED, 10 watt, cool white, driving it at about, as I mentioned, 0.6, 0.5 amps, gives plenty of light and doesn't heat up too much. Heatsink I took off an quite damn ancient motherboard. Let me show you. So that heatsink was located on this beast, which is AMD K5. Man, what a slow machine. It's like first computer in our family. And god damn it, just look at that frequency, 66 megahertz. Oh, God bless. So let's move on to the LED driver again. I say enough rambling, let's show you some demonstrations. And the thing will be encased in this case actually, which is again a base of a CFL with some plastic thingy on the top which will house the driver, and we'll have this heatsink on top of it. And the overall can see height is not that much. Actually, it will be not as tall as the ordinary CFL, so that's a nice feature. And that, in particular, is thanks to this driver, which is quite small. You can see not really tall at all. You can see about just a little more tall than my thumb. No, rambling. Let's give you some demonstration. I'm powering it right now through a 40-watt bulb because I'm testing it, but I tested it basically without any kind of ballast and it operates just fine. I'm just too lazy to unhook the ballast now. So power up, and you can see that current is 590 milliamps and dropping down. Light output is intense. Very nice. And you can see how the current drops. And to prove that it's a thermal issue, I'm gonna give you a quick demonstration. I'll go and blow at this from this side, and you will see that current will raise up. Significant difference, isn't it? So that's it. I'll put it back together and I'll show you again. But that's another video that I'm gonna paste in. It's gonna take me a while, but for you it's gonna be just a few seconds. And I even added common mode choke there. You can see a filter with a 1 amp fuse. 100 nanofarads, 33 nanofarads. I didn't calculate it, I just botched what I have. It will work just fine. The common mode choke by itself will kill some noise, but this capacitor will help even more. Alright, CFL out, lamp in. Let's put it in. Okay, it's in. Let me shut off the light. And turn on this one. Not too shabby, isn't it? 5,000 or 6,500, something in that region. Color temperature, so yeah, cool white version, very nice. Not a neutral white, which is about 4100 kelvins, but still rather nice. I find it actually a very nice color temperature to keep you concentrated on the walk. So cool white, great for work light. If you want just a comfortable light to just relax and read a book, I recommend you using warm white. It just it literally is making difference, and there are some researchers that really proves this, that warm white are actually better for casual, like relaxing light, and cool white is better for work lights. So yet another demonstration, guys. You can see a lamp. Alright, so you won't tell me that I'm showing you miscellaneous BS. It's really a lamp that I was talking about. You can see how nicely it glows. See on the floor, very easy. You can see